Cool. Hi everyone. Geoffroy and I are very pleased to have you over for this first Q&A session organized by IEA Energy Storage Task 45 group. As a small reminder, Task 45 aims to provide the knowledge and framework necessary to accelerate the market uptake of large thermal energy storage, which includes pit thermal energy storage, borehole thermal energy storage, tank thermal energy storage, and aquifer thermal energy storage. So my name is Roman Sush, and I'm working for Planaki alongside Geoffroy Gauthier, and will be facilitating this Q&A session. So during this session, we have invited some experts who will address some questions that have been submitted so far to the group, covering 3 key areas. The first one being planning, legal, and societal aspects of large thermal energy storage implementation. The second being technical aspects, including feasibility, design, tendering, and monitoring. And the third one being practical experiences from real-world large thermal energy storage projects. I will quickly introduce the presenters that will be asked throughout the session to answer our question. So there is John Bergersen and Martin Christiansen from Aalborg CSP. There is Per Alex and Niels from Planenergy, Vrim from AE Intech, Maya Moser from Solid, Bas Gottschalk from DTESS, and Yanis from DTU. So we have listed all the questions some questions that we've got so far, and that will cover 3 main topics. So we'll start with question related to large thermal energy storage design, then large thermal energy storage application, some number 3 different question regarding the cost of large thermal energy storage, and finally some career opportunities. So I guess we can start with the first question. That would be so that you can see here, and that would be for Yanis. I think I've seen him connected. Yes. So the question is here: are phase change material called PCM only used in LTES, or it is conceivable that they are also used in PTES?
Right. So, yeah, I mean, in theory, this can happen. Of course, there is no system that actually uses PCM in combination with a pit storage. However, in practice, I see it being a little bit more difficult, as one needs to keep in mind that the pit storage is not really a closed system. So there's always some water or whatever you have as a storage medium that leaks to the ground. So I could see that if you use a phase change material, it could be a little bit harder to get permits or make sure that it has no environmental impact. So I think that in general, the answer is in theory, yes, but in practice, I can see having a lot of difficulties. Yeah.
All right. Thank you very much for this answer, Alex.
If you calculate economy, then it will be quite clear that it's mission impossible to use phase change materials in PTES.
All right. Thanks for this comment.
Niels also.
Yeah. Sorry.
Yes. The only exception is, of course, when you're using the pitted storage for cooling, then the phase change could be the water itself at 0 degrees.
Thanks for that. Any other comments from experts on this question? Nope. Thanks for that. So we can move on to the second question. That would be for Thomas Schmidt Maya Moser and Alex and Niels from. In East Lothian, Scotland, we are exploring the opportunity to include pit storage as part of a new large-scale district heating network that could eventually expand to deliver 1,500 gigawatt-hour or more. Next to two major heat sources is a quarry of 5 million cubic meters, void up to 4 meters deep, and we have been offered the chance to use part of this for thermal storage. It's cheaper for the operator to leave a void for us than to backfill. So there are two questions regarding this topic. First, what is the most efficient geometry for pit thermal energy storage? And second, are there advantages in our development to plan for more than one pit thermal energy storage as our heat demand grows? What long-term operation benefits might this bring? So Thomas, Maria, and Alex, feel free to raise your hand and answer. Niels, you can start.
Yes, from a theoretical point of view, the best geometry will be ball shaped, but that's impossible for pitted storage due to many reasons. One of them being that we have a water surface which is horizontal. So the next best geometry will be the one which gives us the lowest surface area compared to the volume. And as a part of that, we want to minimize the size or the area of the lid because the lid is the most expensive part of the storage. So in this case, we will say that the deeper the storage can be, the better, because that will reduce the area of the lid. Also, the steeper the sides of the storage can be, the better. Again, that will also reduce the lid. In the storage is built so far in Denmark, the walls are not that steep. It's 1 to 2, so an angle of about 26 degrees compared to horizontal. But that's what is possible when using soil of the Danish kind, at least, and also when building the liner, the workers has to be able to walk on the sides at the same time. For the second part of the questions, whether it will be beneficial to have a very large storage divided into more than one basin, indeed it will. One of the reasons is that a construction work of this size cannot be done in one season, and the liner works can only be done in the summertime because of the weather conditions. So the storage should not be larger than, or each part of the storage should not be larger than it's possible to build during a summer season. Also, it makes sense if you're not needing the complete storage from the beginning to divide it into multiple parts. And also during operation, if you have just one large storage, you will have the high heat loss all year round. But if you divide it into two, you can discharge one part first and then discharge the other part afterwards. So you reduce the heat losses there also.
Thank you very much, Niels, for this answer. Is there anyone who would like to provide an answer or return of experience on this matter? Geoffroy?
So yeah, so Niels said the, let's say, the theoretical geometry that would be ideal. So minimizing the lid area and having as steep slopes as possible. There is also a question, if you work with soil, there's also a question of buildability. So if you want to have the minimum surface, let's say on the sides for a given slope, then you would look for a cylinder. but in practice, it's very complicated to use machines to build a cylinder or a truncated cone, let's say. So you will have to divide your sides into a given amount of sides. And in that regard, what we've seen is that the truncated pyramid, so with 4 sides, is rather simple, because then you minimize the number of angles that you have to weld and to take care of when building the liner on the sides. So that's one practical aspect. And another thing that Niels has said is that this slope of 1 to 2 is what we've seen as an let's say as a favorable condition in Danish context, but it is also possible, and this is a new development that we see. It is also possible to use some techniques to reinforce the soil such that you can have steeper slopes, and you can reinforce the soil amongst other things with the geotextile solutions. So this is something we see in the construction industry when you need to build a road, for example. But this is also something that is being considered for pit thermal energy storage as well. And this is something that is being studied, for example, in the Treasure project.
Thanks for that. Wim? We cannot hear you. You're muted.
And now I'm not muted anymore. Yes,
Perfect.
interesting question, because it's referring to a quarry, meaning that part of or most of the infrastructure already has been dug out. And perhaps it's interesting to look at the experience that is now being built up in the south of Graz in Austria, where an old basalt quarry also is being planned to be used as a seasonal thermal energy storage. Perhaps Maria could tell more about this.
Yes, thank you, Wim. It sounds a little bit similar to the project we have in Graz. There is also a quarry, which in total volume it would be up to 2 million cubic meters if it's filled completely. And one very important thing that we have to look at, and maybe it's a similar, of course, the groundwater is always an important thing with the storages, and also in the quarry. In the quarry, there is so the quarry in Graz will only be filled up beneath the groundwater, because it's also about 40 meter deep, and in about 10 meters there is a groundwater flow. So it will be filled up about 25 to 30 meters high. And also the total volume maybe is important for what is the legal situation. I don't know in Scotland, but in Austria, this stored water should not exceed 2 million cubic meters, because then there are much more, how do you say, safety measures and other things you have to apply. So we try to stay beneath these 2 million cubic meters. This is maybe something that also has to be looked at. And of course, in Graz, also one thing is how to put the lid on the sides of the quarry, because it's not like a pit where you dig out and then you can easily put the lid and build it up beneath the embankment. And in the quarry, we have like almost vertical sides. So there is one thing how to find out to put the lid on these vertical sides. So maybe these are some things that has to be looked deeper if it's not a pit, but a quarry.
Thank you very much, Maria, for this version of experience for the project.
If it's interesting, I could also put the link to the project, the website, in the chat. Maybe I can do this.
Yes, please do so,
good.
and it will be relayed to the group after the Q&A.
Okay.
Thank you.
Yeah, thank you very much.
And actually, in the chat, there has been a further comment from Thomas Lapta from Solmax, saying that the inverted truncated pyramid is indeed the most optimal geometry for reducing the weld seams, making it the best use of liners. And another remark is that laying the sealing membranes during the welding season from around April to October is ideal. The output depends on the capacity of the installer, and in the case of a pit, several embankments can be sealed at the same time. But of course, the earthworks contractor, when there is earthworks that is needed, must be able to provide sufficient output to prepare the subsoil. But thank you, Thomas, for this further comment.
Yep. Thank you very much. Is there any other answer to be given to this question from experts? Well, if not, we can move on to the third question for maybe Per-Alex or Nils-Bram or someone else. How are pits usually integrated in the district heating networks requiring temperature above 100 degrees Celsius? What is the typical temperature range for the storage in these cases? Yes.
Yes, we can start by saying that so far we have not been above 100 degrees in the storages, and we will never come so, because the storage is working at atmospheric pressure. So above 100 degrees, the water will boil. Another limitation is the material used in the pit heat storages. Due to lifetime considerations, we will not have the temperatures above 90 or 95 degrees at any time. The low temperature in the storage can go down to the freezing point of water, but not below that. But it's the high end which is interesting here. So in case we need higher temperatures for the district heating network, then we are possible to deliver from the storage. Then we need some kind of post-heating. The simplest way is just to have a boiler. That could be an electric boiler or any other kind of boiler, which can increase the temperature after the energy has left the storage. Or a little more complicated but more efficient, you can use an electrical heat pump to raise the temperature leaving the storage while cooling the low temperature of the storage at the same time.
All right. Thank you very much, Nils. Giorgio, do you have a comment?
Yes. Hi. Just to answer also this question, there's an interesting project in Vienna where they are trying to build an underground storage using the heat pump in order to feed their grid that has, if I'm not wrong, 120 supply degrees supply temperature, and they use the heat pump. So, and surely you can find some documentation online about this.
Thanks for that, Geoffroy.
Yes, I think this might be one of the demonstrators of treasure there. In the same way, and it's not for an application above 100 degrees Celsius, but in treasure, there is also one pit thermal energy storage that is operated at rather low temperatures. It's charged up to, I think it's 67 degrees is the maximum temperature in Poland, in Lidzbark-Waminski. And there, the temperatures on the network are obviously higher than this in the winter. So they are currently using a heat pump to increase the temperature from the storage to what is required on the network. So in a similar way, using a pit thermal energy storage with higher temperatures such as we already see today in Høje-Taastrup or in other pit thermal storages in Denmark, for example, then you could have a high temperature heat pump taking this rather high temperature, 80, 90 degrees, up to something that is above 100 degrees with a heat pump. And again, as Niels said, it can be done with a boiler. It can also be done with an absorption heat pump. So it really depends on what kind of system design you want to do, and also what kind of available extra auxiliary heat sources you have.
Yeah, thanks, Jofa, for these comments. Last, Ahmed, do you have a comment?
Yeah, actually, I would like to just refer to a point, as already mentioned, about the heat sources that can be combined with the BTS. So it's like the thermal energy storage from Kraftwerk at the moment. It can be used in order like to gain heat into the storage at the when the prices are very low, for example, and then you can all the time discharge this amount of heat in combined to the level that it's required. So it's a combination between the thermal energy storage from Kraftwerk, for example, which is can store heat at higher temperatures, then combined with this kind of source. I think it would be a good combination for such an application. Yeah, thank you very much.
Thanks for that. Is there any other comments or answer to be given to this question? If not, we can move on to the next question. Just before that, I'm sending in the chat a link of the form where you can just add some questions if some comes in your mind that would be answered either at the end of this Q&A session if time permits, or just in the upcoming one. We can move on to the fourth question. So I am interested to find out more about engaging with the flexibility market and storage. With flexibility, the electrode border approach is being considered, but we also have a 1 megawatt heat pump that can be used. However, the heat pump is far more delicate than an electrode border, so the person is keen to find out how others have used their heat pumps in this market. Perhaps Alex or Niels can provide an answer to this question, or other experts. Alex?
Yeah, I can try. We have in Denmark several heat pumps connected to tank storages, and they are operated on the flexibility market. All of them are operated on the day-ahead market for the variable electricity prices, but also some of them are operated on the balancing markets. So if they can, for instance, upregulate within 15 minutes, then they can give bids in the balancing market. So that's our experiences until now. And of course, you can use also heat pump combined with pitters in the same way.
All right. Thank you very much, Per. Is there anyone else who would like to provide an answer to this question? Yeah, Niels?
Yes, I think you should be aware of that there finds different kind of heat pumps technology, and that's mainly due to different refrigerants and different compressor types. So when you are ordering a heat pump, you should be aware of what you want to use it for, because some kind of heat pumps are not suitable for participating in the fast electricity markets.
Thanks for that. Any other comments on this fourth question? Nope. So I guess we can move on to the next one. So as some time has passed since planning and construction phases of the storages, due to different influences, construction costs have increased enormously. How is the influence to the heat generation costs, and how is there a guarantee that the prices for the end users are not increasing too much, since it would make district heating very unattractive? Who would like to take this one? Alex?
Well, I can start. I'm not quite sure that I have understood the question right, because I think that it's not possible to give a guarantee for future prices. Unless for the storage, of course, when you have seen the tendering results, then you know approximately the future price, and that's you could say the costs in the beginning for a Peters, for instance, they are very high, and then the operation costs are quite low compared. So then there you know the future cost of storing. But the cost of production of heat is, of course, depending on the source. So if you have solar thermal, then you pay nearly everything from the beginning, and then you know the cost. And if you have direct solar and wind combined with heat pumps, for instance, then also you know the cost because you have the investments in the beginning. But if all other kinds of, you would say, if you have a heat pump on the electricity market, you don't know the future electricity market, so you can never guarantee a future price. But what's interesting here is that the competing technologies, for instance, individual heat pumps, it's not possible either to guarantee the future price there. So it's the conditions for the heating market.
All right, Alex, thank you very much. Anyone else? Has anyone else a comment or an answer to give to this question? Nope. So we can move on to this question number 6. Are there any examples of true seasonal storage installations, so like with 2 or less cycles per year, that achieve a low levelized cost of heat? For example, somewhat competitive with alternatives. What are some of the main cost reductions foreseen in the future? So maybe either Niels, Alex, or Martin, or John from our box SB could answer to that. Answer this. Yes, Per?
Yeah, well, we have 5 examples of Peters in Denmark where we combined solar thermal with Peters, and for all of those, they were actually feasible when they were installed. So the reason why we're not doing this anymore is that now the electricity prices are so low that the electricity fuel heat pumps are actually cheaper than the solar thermal. So but it was possible. But in Denmark, you have to know that we have a heavy tax on fossil fuels. So that's one of the reasons why this was feasible. For the future, well, I can only see I can mention one thing where I think the cost reduction can come in, because now we pay quite much for treatment of the water. So if we can avoid corrosion, the corrosion risk, and then avoid expensive treatment of the water, then we could maybe save 10% of the investment cost.
All right. Thanks. Geoffroy?
Yeah, thank you for that, Alex. I think another potential cost decrease in the future would be let's say a better development of the technology providers and the contractors that actually can do this kind of work. Because so far we only have a handful of projects, 10, 15 maximum, in the whole world. And the more this technology will develop, the more technology providers will try to get into this this field. And I think that could potentially bring the prices down. And another fact is that I was mentioning it earlier. The technology itself, such as soil reinforcement, are still being developed, and there are research projects, for example, in Germany, looking at potential new design of pit thermal energy storages. So I feel like the technology can still evolve and improve, and that could also lead to some cost reduction. So not only for the corrosion-free, but also on the design of the pit thermal energy storages themselves, using a steeper slope with soil reinforcements and other innovations such as this. And yeah, this is what I foresee, and I think Thomas Schmidt can tell us a bit more about this research project in Germany. So I'll leave the floor to Thomas.
Thank you, Tori. Yeah, I don't want to go more in detail on this German research project. I think there are quite a number of projects ongoing that are trying to improve the technology and reduce cost. I want to mention maybe another aspect. When comparing costs of alternatives, it's always important to really look in detail what is being compared. And in the question, there's mentioned some competitive alternatives, and I have the experience that very often not alternatives with the same quality are compared to each other. So if we, for example, take the example that Per Alex mentioned before, a seasonal storage combined with a solar thermal system, and if this one is compared to a fossil-based production system, then the cost might be cheaper in some cases for the fossil-based alternative, but the quality of the two alternatives in terms of CO2 emissions, renewable energy share, and so on is of course not comparable. And so this higher quality of some alternatives has to be considered as well. And a second aspect is also that large storages, they have a high investment cost, but a very low operation cost. So also the time period for the comparison is an interesting aspect to look into, and also the risk of changes of cost of alternatives in the long run has to be considered.
Thank you very much, Thomas, for that. Martin?
Yes, hello, can you hear me?
Yes, we can hear you.
Okay, so just regarding some seasonal storage installation that somehow manage to get a low levelized cost of heating could be Dronninglund, as we have here in Denmark, where basically if they need to receive this low cost, it's also very important to look at what other systems they have to work with the PTES. For example, Dronninglund, they both have a heat pump and also the solar thermal field, which they then can use to charge the PTES, but then also the heat pump can cool the PTES down. So they utilize the PTES a lot more and also get that extra megawatt of energy out of it instead of just cooling it down to 40 degrees. Then it can actually cool it down to almost 10 degrees by utilizing the heat pump. And then, of course, then you get a much better price for the PTES and heat than without the systems. So, yeah, hope that answers a bit.
Yeah, thank you very much. Niels?
Yes, just a short comment to the Dronninglund. In the question, the question is actually true seasonal storage. So it's per definition a single cycle per year. In Dronninglund, the capacity of the storage is only 1/3 of the solar thermal delivered to the district heating network. So it's not a true seasonal storage in that perspective. We see other projects in the southern part of Europe where all the charging is in the summertime and all the discharging is in the wintertime. And there it's true seasonal. And it's actually, in my opinion, not possible to get a very low levelized cost of heat for true seasonal pit heat storage. A very simple napkin calculation says that if the water cost is 40 euro per cubic meter and you need 20 cubic meters to store 1 megawatt hour, and you will have a lifetime of 20 years, then the storing cost for storing 1 megawatt hour for 1 year will be 40 euros. So not taking into account heat losses or cost of the heat going into the storage, but just for the storing cost, it will be 40 euros. And I cannot see it can be better than that as long as you are using just a single cycle a year for 20 years.
Thanks, Niels, for that. Is there anyone else who would like to provide an answer or give a comment on this topic? Geoffrey?
Just a quick comment. One way to make this seasonal storage case better in a way is to have, let's say, a high heat demand potentially all year long with also a high irradiation. If you look at the solar district heating application. And this is one of the examples that we've seen with a purely seasonal storage in Tibet, where the storage was built in a very high altitude place with a lot of a very high solar irradiation, yearly solar irradiation, and still with a high heat demand. So in that case, they were producing a lot of heat with a seasonal storage, but also with a big heat demand. So in that case, it was a good match. But as Niels said, the more cycles you make, the better it is. So it's better to try to plan your storage for storing more than just purely seasonal. And one way also to do this is not to have only heat demand in the winter, but also heat demand all year long. So for example, instead of having only heating, let's say you're connected to a district heating network, then instead of having only space heating with your district heating network, then you could also have domestic hot water, which has a heat demand all year long. And in that case, you will also use part of the summer heat that is produced that will be used from your storage and from your heat production. And in that way, you already get a better economic balance.
Great. Thanks for that. Any last comments on this question? No. So we can move on to the 7th question. So where can I find resources that help me assess the suitability of an area for aquifer thermal energy storage? Are there Europe-wide maps that shows this, or can maps showing other geological information provide an indication of where or where not this might be feasible? Are there examples of LTES, BTES, PTES storing at 80 degrees or more? And what's the end use of the heat in this example? And finally, what are the ballpark costs of this type of storage, range in euros per kilowatt hour, and what companies in Europe deliver this type of thermal energy storage? So maybe best Alex Niels from could at least provide an answer to these questions.
Shall I start? My name
Yes,
is Bas
you can.
Rotsbroek. Sorry. And I have my company LTES, which is specialized in the development of LTES systems in Europe and other countries. So happy to start to answer this question. And my focus will be on LTES, but also we can say more about the other technologies. The first question is about the feasibility map for LTES. There are in a number of countries visibility maps which are freely accessible. The maps are generally based on hydrogeological information, but it depends a little bit from country to country how detailed the maps are. So, and what kind of data has been used to fill the feasibility map. I see that on one side, it depends a little bit on the grid, on are they using drilling data, can you make cross sections? So the level of detail depends from map to map, but at least gives you a first idea of the feasibility. And my recommendation will be that if you have used one map, then please contact someone who has more insight in the interpretation of the geological data to come up with a better assessment. I have found some websites which I have shared with Romain, so I think afterwards there will be links which can be shared. I know that in the Netherlands you have the WKO tool, which is the LTES tool that gives information about the potential for LTES system in the Netherlands. There is a Belgium map which is called Smart Geotherm. There you can assess the open wells, the LTES system, but also the closed loop, the BTES systems. There is a map in Ireland, which is open data and geodata. ArcGIS map, where you can have a more rough indication as far as I know. In Germany, they have a Google-based map where you can see where are the best regions to apply LTES. And I know in UK, I found the GSHP screening tool, which also gives insights. And maybe there are also in other countries some feasibility maps, but this is at least what I could find for today. I hope that will help, and else please contact me. Are there other examples of LTES, BTES, and PTES storing 80 degrees or more? Yes, they are. I think it's interesting for the one who asked this question to have a look at the task 39 results, because in the previous task we investigated as consortium already and summarized actual projects. For an ATES example, I would like to mention the Middenmeer project in the Netherlands, where heat will be stored at 87 degrees. That's the surplus of deep geothermal heat, which will be stored at around 360 meter depth and then reused for heating a greenhouse. For the BTES project, I know that the Drammen in Norway is a good example, but I do not have the details. Maybe someone else can explain it. And I think the BTES is the Droenenlund is already mentioned, and there are more projects, I think, in Denmark. So that about that question. And the last question, which is in fact two questions. What are the ballpark costs? Also in the previous task, we have made a fact sheet, which you can download, and in the fact sheet then an example is described, and also there is a cost indication given in that fact sheet. To summarize it for now, I know that the high temperature ATES system has a cost indication of between 0.1 to 1.3 euro per kilowatt hour. For BTES, it's 0.6 to 3. For BTES, it's 0.4 to 0.6. So, but that is very roughly because it depends very strongly on the location, on the dimensions, on the local situation, on so many factors. But that gives you at least a first mark. And what companies to deliver? When I look at the ATES systems, then you see that there is not one specific supplier in the Netherlands who provide ATES, but there is a complete ecosystem of companies. So you have companies who are more specialized in the design of ATES systems. You have a range, you have some suppliers like the screens or the heat pumps or other equipment which is necessary. You have drilling companies who will make the boreholes and install the wells. You have ESCOs who are running the systems and send the invoices to the end users. So there's not one specific company, but there are more companies and institutes involved in the development. And I think for BTES, we know that in Europe, in Germany, France, and Sweden, there's the highest rate of the highest numbers are installed. So that's maybe good to look there. For BTES, I think you have to be in Denmark to find good companies. So I think that's the first, not very short, but at least the first answer to this question. Thank you.
All right, Bas, thank you very much for that. Niels, Alex, could you maybe provide an answer for the BTES part? Yeah, Alex.
Yeah, the Danish storages with solar thermal, they reach 85 degrees or something like that during the summer months, but not the whole year round. For the storage in Høje Taastrup, it's 90 degrees the whole year round. So that's, you could say, the only example where it's 90 degrees the whole year round. For the prices, I know that Solites and Thomas made a nice curve, or nice curves some years ago, showing the different kind of storages and the prices and the sizes. So I don't know if you can share that, Thomas.
Yeah, I think this graph you're referring to is also included in some of the task 39 fact sheets or deliverables that Geoffrey just gave the link to, and it's available there. In principle, the investment costs refer to either kilowatt hour or size of the storage is depending very much, first of all, on the size of the storage. So it's a big difference if we are talking about a pit storage with 200,000 cubic meters or with 10,000 cubic meters. So that this has a large influence on the cost, and also the storage concept. So is it ATES, BTES, PTES, or TTES has a certain influence. But we found, on the other hand, when we look into this graph that you're referring to, that for the big storage sizes in terms of cubic meter water equivalent, that the PTES concepts somehow shows the most realized projects in really large storage sizes and capacities.
Thank you very much, Thomas. Niels?
Just a short note on the borehole storage. Seeing temperatures 80 degrees or higher, yes, the soil can withstand it. If you're using pipes, which also are able to withstand 80 degrees, not a problem there. But the problem is that the surface area of the pipes in this closed loop system is very small compared to the distance or the volume of the borehole storage. And therefore, if you do not have all the time in the world to charge and discharge the storage, you will have a huge temperature drop, first when charging and then secondly when discharging. So you're not getting the soil up to the same temperature as the water when you're charging, and you're not getting the water up to the same temperature as the soil when you're discharging. So there you should expect a very low temperature out of the storage, even though the energy is stored at a higher temperature.
Thank you very much, Niels. Prince Will, do you have a comment?
More or less, hello everyone. It's more or less like a curiosity. Everything here is about the LTES, the aquifer, the borehole. I just wanted to know how deep the borehole will go. And the case study of about 85 degrees in the Netherlands, or where did you say? Why only 85 degrees? Now, the background of this question is my current thesis at the University of Padua. We are working on deep geothermal energy storage, and we're working with a dual, with a photovoltaic system and a closed loop geothermal system. So we are literally preheating the water to as hot as it can be using solar photovoltaic energy, then injecting it at more than an excess of 100 degrees centigrade down. So why is it limited at 85? Is it a standard? Am I doing it wrong for my thesis and the likes? That's my question.
Bas, go ahead.
Yeah, well, in your question, it was about BTES, but also question about the Netherlands and ATES. So I can tell a little bit more about the ATES project we have in the Netherlands. That is storing the heat at 360 to 380 meters depth, but that's because there was a suitable aquifer where we can store heat, covered by a thick clay layer, which acts as a kind of insulator so that the heat will be kept at the same place. Why 87 degrees? Because that was the output temperature of the deep geothermal heat. So that was the highest temperature we could get, and then we store it, and then we get it out with slightly lower temperature, and then we can go down till 50 degrees to have a direct heating of the greenhouse. I'm also working on another project where we have slightly lower temperatures, also feeding by solar collectors. But it depends every time from case to case what will be the most optimal business case or energy concept, depending on what kind of heat is available, which temperature do you would like to store it, or which temperature can be abstracted and can be delivered direct to an end user, or do you still need to increase the temperature by using a heat pump? So is the heat pump a part of the energy concept, and is it before storing or is it after storing? So there are many options to create your project, and I will not say that one is good or the other is wrong. It depends very strongly on what is the goal of your storage. I've also checked to see if you can maybe have high temperature storage at 120 degrees. That was for a project to combine it with district heating networks, because then it will have an advantage to have higher storage temperatures, but then you also need higher pressures to prevent the boiling of water. So yeah, in some locations, yeah, you have a shallow aquifer, which is better. So it really depends from case to case.
Sorry. Yes, it's fine. Thank you very much. Lastly, for a young professional, someone of my status, of all the speakers today, I don't know if their companies would want to work. Do they have an opportunity for people to be attached to integrate this knowledge into their theses and the likes?
So actually, this is we have this question listed as question 9. So maybe Romain, you can skip to that. No, but you can go directly for that, because the time is running out for this Q&A session, and we will not be able to go through all questions in all sessions. So I think we'll open this question up for closing today's session, and the questions that haven't been answered will be answered in an upcoming Q&A session, which will be in November. But please, for the experts that are present, maybe Wim, you have some insights to give for this question to what are the career opportunities for PhD holders in this field?
And masters too. Thank you.
Yeah. I think the career opportunities are very diverse. The market is growing. We see an upcoming of more projects, and also opportunities for young people to come in this field. There is what we do if there are vacancies, then we will distribute them as much as possible. And you could also check, say, the website of IEA Energy Storage Program, in which there will be also vacancies for at least PhD programs. And for the rest, I think it's a wide field, and there's a lot of opportunity for young experts to come in.
Yeah, if I may add to what Wim has said, one way you can use this IEA Energy Storage website is by looking at the tasks that are active at the moment. And then usually most tasks have a description of the companies that are involved in the task. And from there, you can get an idea of what is the activity of the partners, and also potentially a contact to what is being done. The good idea when doing this is that when you have access to, let's say, Task 45's webpage, then you can also see some of the work or some of the publication or some of the presentations that have been done. So you already have an idea of what the people are doing on the side as a part of this work. So it's a good idea to try to go through these networks, and then maybe find the people involved in the different projects, and then reach out to them to see if there are opportunities there. So I think this is it for today. We've run a tiny bit over time, but if we can go to the last slide showing the upcoming events from Task 45. Yes, this slide. So today we've been through our first Q&A session, but the next Q&A session will take place in November, so stay tuned. We will try to still gather the questions that have been asked through the form and that haven't been answered yet. And then the questions and answers will be published on the website of IEA Energy Storage Task 45. So thank you everyone for participating today. Thank you for asking questions. Thank you for the experts for answering them. And we wish you a pleasant day.
Thank you very much.
Thank you.
Bye.
Thank you. Bye-bye.
Thank you.
Thanks a
Bye.
lot. Bye, everyone.
Thank you.